Lots of people are joining us online, apparently. Welcome. I cannot hear you, unfortunately. Hopefully you do. So how do we do this again?
You need to go onto slideshow.
Is that all right?
Yeah, that's good.
Lobby.
Yeah, you are.
People coming. Okay, last round of admissions. Admitting. Okay. Thanks for coming, everyone. This is following concerning news. It's on everybody's mind. Military action is happening in the area where there's nuclear power plant, and there are lots of opinions and interpretations of what's going on. So I thought it will be useful for the community to sort of have a view of technical issues without expressing opinions on particular implications that might be of this technology to, I don't know, politics or outcome of the war. So it's going to be very impartial and completely about sort of technology issues, what to expect of some speculations what might happen, but speaking from kind of science and technology perspective. So to set the scene, the nuclear power plant in Zaporizhzhia is of this type, pressurized water reactor with 3 cooling loops. So we've got, let me point maybe on the screen. So few things that will be featured throughout this this talk. So learning the vocabulary first. So the heat is born in here. You know, there's a glowing redness, and being moved to secondary cooling circuit by water. So we are pumping water that picks up the heat and gives it off in a primary side of a steam generator. On the secondary side of steam generator, steam is being generated, as the name suggests, which then drives the turbine, and 1/3 of the heat, roughly, is being converted to electricity. The other 2/3 have to be rejected to the ultimate heat sink, and this is where many nuclear power plants in the world differ somewhat. Size will be, for example, the closest one to Cambridge uses seawater that is pumped to cool the condensers that will condense the steam coming out of terminal of the turbine, partially condensed steam. So the primary circuit and the secondary circuit are completely sealed, so there is no mass exchange between these two, only the energy exchange. So the reactors we're talking about, the kind of unit of account is gigawatt. So gigawatt is 1 million megawatts of power, which is pretty large amount. And for 3 gigawatts of heat, we're producing 1 gigawatt of electricity. Therefore, 2 gigawatts of heat have to be dissipated to the environment. So in size this would be North Sea. In the case of Zaporizhzhia, we'll talk about in a moment, because the answer is somewhat complicated. And this is one of our primary concerns. The only other thing to point out here is this thing called containment structure, which has nothing to do with heat removal under normal operation, but it performs important safety function. So there's a kind of nuclear mantra of 3 C's, controlling chain reaction, so that the heat produced through fission is at a controllable rate. Then cooling the core, because if heat is not removed at the same rate as it's produced, then things will heat up. And the third function is containment. So if things do go wrong, then radiation that might have been released needs to be contained. So there needs to be a barrier between environment where it can hurt people and where it's generated. So containment will also feature in the talk later on. So the power plant has 6 units. They're all identical design. So the Russian version of pressurized water reactor, known as VVER, and the modification is relatively old one, so one of the earlier ones of that power, called V320. This is the largest power plant in Europe and the 9th largest in the world. It was brought online within a decade, so all units, speaking of nuclear is slow, at least in the early days it was possible, not only in the West, but also within the Soviet Union. So 85 is the first unit brought online, and 1 unit every year, apart from the last one, which took a little longer. So these units, they all sit in a row. I will have a more kind of detailed picture talking about individual components, what we see on this slide. Another piece of essential vocabulary that is featured in many news reports is these 2 useful definitions of hot shutdown and cold shutdown. So shutdown implies that chain reaction has stopped. So there is no fission happening in reactor cores. So at the moment, all 6 units are shut down. So there is no fission chain reaction happening. The difference between hot shutdown and cold shutdown is essentially how fast do we want to restart them. So if a break in reactor operation is short and there is anticipation of bringing it back online, heating up, warming up all the systems may take a while, so days essentially, maybe 3 days, between when everything is depressurized and cold, or kind of room temperature, all the way to operating temperatures and pressures. That takes 3 days. So if you want to restart relatively fast, within hours rather than days, then people will do shutdown, but hot shutdown, without depressurization of primary circuit. In that case, so we call it a hot shutdown. At least initially, the heat can be dissipated through the main heat exchangers, meaning steam generators, which can generate steam and which can bypass the turbine and dump it directly to condensers. But as heat is gradually reduced, then dedicated decay heat removal system takes over with a dedicated heat exchanger. So steam generators are not needed to provide that. And at low power, steam generators can also operate in a natural circulation mode, where the circulating pumps, each one is on the order of 5 megawatts of pumping power. So the primary water takes 20 megawatts of power to circulate, which is quite impressive for those who, I know, Alex, you impressed? But, yes, so after fission chain reaction is shut down, reactor continues to generate heat. This is because after a while, when enough fissions have happened, fission products are overly rich in neutrons, therefore unstable, and tend to give off that extra energy by radioactive decay. That decay, each decay has some heat associated with it. So some energy is released in every decay. And because there are many of those fission products, they all have their time constants with which they decay. The heat produced by shutdown reactor cores is non-zero. So initially, after a second after shutdown, the decay heat is on the order of 5% of nominal power. So if we had 3 gigawatts of 3,000 megawatts of power, 5% of that is sort of 150 or 15. 15, yeah. 15 megawatts per unit. So there are 6 of them, so there's quite a bit of heat. But important thing to note here that all units have been shut down for a while, for months. The one that was shut down the shortest time ago, that was, I believe, in September last year. So there's good few months, so let's say more than half a year has passed since the fission chain reaction was stopped. So at the scale here, so the x-axis is in seconds, but for your convenience, seconds are translated into hours, days, weeks, months, and years. So we're somewhere between months and a year, which means the decay heat is on the order of 0.1% at the moment per unit. So that's a number to remember.
So just confirm what P is. Is P pressure, P reactor?
P as power.
It's power.
It's power divided by nominal power.
Okay, that is power. Okay.
Yeah. So initially, after 1 second, we're on the order of 5, 6.
It's just a matter of what P, the definition of P is.
Yes. Yeah. So the last thing I want to mention in kind of theoretical prerequisite for the story is sources of stored energy. So again, if rate of heat production is not matched by rate of heat removal, things will overheat and destroy themselves. So that's just the nature of the things. And since initially the decay heat is quite substantial, this is the greatest evil or the greatest concern for reactor safety system design and eventual operation. So you can see here that integral decay heat, so if we integrate that into energy over first day following shutdown, it's by far the greatest component of the entirety of stored energy that we have to deal with. So other important sources of stored energy is pressurized primary and secondary systems. So they're both high temperature, high pressure. So they have quite a lot of stored energy because of that. So this is relative to, let's say, ambient conditions. So 1 bar of pressure in room temperature. So the good news is that since all reactors have been shut down for a long while, and they are now in so-called cold shutdown, the term that we know by now, the first 3 components of stored energy has largely been eliminated. So they're essentially gone. Decay heat is much smaller, but not non-zero. So we have an order of magnitude reduction in decay heat. And primary and secondary systems are depressurized and at roughly room temperature, below 100 degrees C. Other sources that are quite interesting and might become relevant are exothermic reactions between components that sit inside the containment structure. So the most important ones is zirconium reaction with water or steam. So there's lots of zirconium because that's the cladding of typical nuclear fuel, including Russian fuel. After about, or at about 1200 degrees C, that reaction becomes exothermic and self-sustaining. So the cladding will essentially burn in steam atmosphere, releasing heat. And most annoyingly, it will also release hydrogen, which can then burn itself by itself and release even more energy. So that's why these other 2 elements reacting between themselves, and then secondary reactions of the reaction products with oxygen. So all these may be concerned in the future. Now to some pictures of what's going on. So this is a satellite picture just before the dam was blown up, and this is important to understand sources of cooling water. So the decay heat is small, but it's not negligible. And again, if it's not removed and the rate of removal is not matched or is not matching the rate of production, then things will overheat, and overheat to temperatures where this zirconium cladding, for example, will react with water. So what you see here is the 6 units lined up here. So I don't know if you can see my mouse. Can you? Yeah. I'm pointing this on my slide on the screen so that people online can also see that. So remember that tertiary circuit, which in size will be is seawater. In case of Zaporizhzhia Nuclear Power Plant, it has multiple sources of that cooling. So in addition to 6 units of nuclear plant, there is a thermal coal burning plant. I think it's coal. Maybe I'm mistaken because there's no pile of coal nearby and no obvious way of bringing it here. Is it coal? Yeah, it is coal. Anyway, so just like any other heat engine, it also requires cooling. So what we see here around this coast is the reservoir, water reservoir, with these channels being intake of water to cool condensers of the thermal plant. So this is a pretty wide channel, which then goes all the way into here to feed this cooling pond, which by itself is a complicated structure, but that's our main point of concern. So the feed into that pond is through from reservoir through the thermal plant, through this channel again, and into the cooling pond of the nuclear plant. So close up. So just to, again, the nomenclature, what we call things. So reservoir, Nova Kakhovka, Kakhovska, how do you call it? Nova Kakhovka, or just Kakhovka?
I think it's Nova Kakhovka. Kakhovka is.
Right, yeah. And cooling pond and the six units.
Sorry, Kakhovka, new Kakhovka, it's just
a city, yeah, yeah.
It's not reservoir, it's river. This is
Yeah,
reservoir for
yeah, but the dam created водохранилище.
Водохранилище, yes, but it's river.
Yeah. It's yeah, exactly. So this is.
Below.
No, we'll get there. Don't jump. Yeah, don't spoil the story. So Dnipro River, Zaporizhzhia, by the way, means beyond rapids. So it was like following in rapids, and Zaporizhzhia or Zaporozhye in Russian means like beyond rapids, right? So this is Dnipro River that was obstructed here by a series of dams, creating these reservoirs. On the shores of one of them, a power plant was built. So, we'll, for the purposes of this talk, we'll call it a reservoir. Okay, yeah. Now, on the site, what we see here is 5 units. So the containment buildings are cylindrical. You see them here. The rectangles attached right next to those are turbine holes, so 6 turbine holes. Each unit has 3 diesel generators that provide emergency pumping power. So in the case of loss of power to the plant, off-site power, these diesel generators will kick in and provide all the necessary loads, including, or most importantly, pumping power for cooling. Now you can see here, each unit has a pumping station that brings water from this channel that borders the cooling pond to turbine condensers. Then we have 2 buildings that take care of low-level waste. So reactors produce, things like gloves and ion exchange resins for like cleaning water. They're mildly radioactive, so they need to be managed responsibly. Then another option for decay heat removal is so-called spray ponds that we'll see in a moment in the next picture. But when I was talking about dedicated heat exchangers taking over steam generators when removing decay heat under shutdown conditions, this is what I was talking about. So in this particular plant, this is done through this spray ponds, little fountains that essentially make spray hot water coming from the condenser, increasing its surface area, and then as it falls through air, it cools more efficiently than just by dumping it into water. So spray ponds. Then spent fuel from these units is stored initially in cooling ponds next to reactor, so inside reactor building. We'll see a picture in a moment as well. After a short while, on the order of a few years, the fuel is cold enough, so the decay heat is reduced sufficiently to put these spent fuel assemblies into casks that are cooled by natural circulation of air. So they can maintain their safe temperature when cooled by natural circulation of air. And these storage casks is relatively new invention because when the plant was originally designed, the intention was to reprocess that spent fuel, and it was all taken to Russian reprocessing plant. But since 2000 and a bit, these contracts stopped, and the cooling ponds next to reactor pressure vessel were full. And the Western practice is to put spent fuel in these air-cooled dry cask storage. So that facility was built, and it's located in here. Now, the training center that was featured in the early days of the war, many of us have watched this in real life. It was very busy night. So the simulator and training center and the switch yard with lots of transmission capacity. So there are 3 high voltage lines at 330 kilovolts and 4 750 kilovolts. So this is it's a big plant, lots of transmission capacity. When I say cooling spray ponds, so this is what they look. It's a relatively recent picture. You see IEA people walking around it. So at the moment they are not blowing that water at full capacity. So they've, ordinarily it's much more vigorous than this, but you get the point. So a pipe with a sprinkle and hot water coming out of it, and gets cooled by this way. Another picture, I'm not sure why it's here, but just another angle at the plant where you see all 6 units. Each unit has a stack which would, in case of overpressurization of containment building, which might happen, so it actually can hold up to 3 or 4 bars of pressure. Bob, correct me if I'm wrong. You might know the number.
I don't know for this one.
Well, a typical PWR pressure, which is being regularly tested, and Sizewell B, they do these tests regularly. So 72 hours or some few days of pressure with very low requirements on leakage rate. So, but they do have finite design pressure. So if the environment within the containment gets close to that value, then there's an option of controlled venting of containment atmosphere through filters into the stack. With all the important fission products will be normally scrubbed by doing this. So we'll get to that in a moment as well. So now speaking about assaults, again, early days. So this is a training center. which ironically trained lots of Russian operators as well. This is a very large plant with lots of operators coming through, and they're doing this so regularly in such a large basis, so it became a well-known, high-quality training center for not just this power plant, but also other power plants. So the Unit 5 was in hot shutdown, providing some heat to nearby town, which I should have mentioned. Let's go here, maybe. Yeah, so the town of Enerhodar is where, just a city where people live. There's some industry, not just the power plant. Relatively large city, which also has a district heating pipe supplying hot water to the city. There's lots of shelling, so in close proximity of the unit. So here's IAEA Director General inspecting one of those hits, and there were many attempts to damage the transmission lines. So luckily, all of these damage events have been repaired within days. So at the moment, because of such a great redundancy in power supply, it's been working well so far. So a lot of transmission capacity. That's the main thing. So now getting to the main event of concern that basically that's why we're all here, is the explosion on Kakhovka Dam, which is about 120 kilometers down the river. And the concern is that as this obstruction is no longer there, the river returns to its original route, and all that water, first of all, floods the territories down the river, creating a major environmental disaster. So with lots of casualties and environmental damage. But also the cooling pond that was drawing water from the reservoir is receding, or has receded quite substantially, to the point where there is a real danger of that cooling pond not being able to be replenished with new water. So we'll do some basic arithmetics in a moment, how much water would be needed. So this is a relatively recent satellite picture. So this is on 5th of June, just before the explosion. So this is the outlet of the cooling pond. So water coming in and out routinely. So 2/3 of the water is replenished just to maintain the water quality, so the health of the cooling pond. So this is the outlet with some gates in here. So we'll talk about the relative elevations of various things as well. So a few days later, so 4 days later after the explosion, you can see that water started to recede, and that cooling channel is already completely dry. So if there is a loss of that capacity to contain water within the pool, some of it can also be lost. Luckily, the channel is relatively small, and just shoveling a bit of dirt over that channel would create enough obstruction for not to lose that cooling water. So this is also one of the recent pictures. So this is the original route of the Dnipro River, which is sort of returned to where it used to be, and all that used to be flooded plains, And as you can see, the water around this cooling pond is receded quite far away. So when we started to look at how this pond is actually being fed, it's not apparently that straightforward, and it also changes depending on which type of the weather there is. So summer and winter modes of operations are different. So one thing I failed to mention is over here. So there are these two little dots on here. You may barely see them, but these are cooling towers. So cooling towers can each dissipate several gigawatts of thermal power. These are one of the also largest in the world, 120 meters tall. So as small as they are actually the main heat sink, ultimate heat sink for the power plant.
These are atmospheric cooling towers, are they?
Yeah, natural draft. Yeah, so that's why they're so tall. So these cooling towers are available and they're working all the time. So the only time they are not needed is in the depth of winter when the temperatures, ambient temperatures drop below minus 10 degrees. Then they can be, like all 6 units can be cooled through cooling ponds and without the cooling towers. So cooling towers are much more efficient, but more expensive. And those sprinkles are very cheap, but not as efficient. So that's, and the real limit is the temperature of the cooling pond, which if it reaches 30 degrees or more, then it impacts the vacuum of the condenser and then reduces efficiency of the power plant. So that's the real limit. So keeping the cooling pond temperature below 30 degrees is you can do that by managing how much heat you dump into the cooling towers versus the cooling pond. So the way it works, yeah, here you go. So this is the only schematic kind of that I was able to find. Our main heat sinks are cooling pond and the cooling towers. So they are working in tandem with emphasis on one or the other depending on weather. The cooling pond is fed through that channel that goes first through the thermal plant, then spills into the cooling pond. Then again, to maintain the right chemistry or the health of the cooling water, a large proportion of that is being released back into the reservoir. And roughly 1/3 is being evaporated or carried away by droplets as they go through these sprinkles. Yeah, let's do this here. So remember these pumping houses, the little sheds that house pumps to feed condensers. So this inner channel is where the water is drawn from into the condenser. It picks up the residual heat. And then the heat is dumped into the second, or water is ejected to the second channel. Part of it spills directly into the pond through some sparging pipes. And other part is going through this channel under this dam and through a series of yet other sprinkles. So, which are then pick up this hot water and after cooling it through air, it becomes cold again, and some of the cooling pond cold water is picked up here as well, and then it returns to the pumping houses. So quite complicated scheme, but everything is there for a reason. So going back to our scheme. So there's incoming channel and outgoing channel. So those two that go along the units. These are turbine condensers that draw it from incoming channel and put it into outgoing channel, then back to the pond. And then there's a fork. So some proportion of it goes to cooling towers, some proportion goes to the cooling pond. Right. So that's not me. Something like this, I said several times, but there is every year the balance of water is slightly different, but the big picture is relatively standard, relatively the same. So total water consumption is about 300,000 millions of cubic meters of water per year. 1/3 of it is lost to evaporation and droplets being carried away by wind and trained into the atmosphere. A tiny proportion of it, something like 1%, actually seeps through the dam, so it's not impenetrable. It's leaky, but the leakage rate is about 1% a year. So that's not a terribly big deal in here. And then the 300,000 are made up by intake from that cooling channel that feeds off the main reservoir through the thermal plant into the cooling pond of the nuclear plant. So, and then there's some small change used for other things, but 2/3 at normal rate of operation. The number to remember is this 100,000 million cubic meters of water that is needed to dissipate 3 gigawatts per unit, or 2 gigawatts per unit per year. So that's the budget that we've got within that cooling pond, essentially. So this is some other ways of looking at it, or to see where the danger lies, essentially. So on the left-hand side, or your left-hand side, this is a reservoir. I think it was the dam was blown when it was at 17 something meters, so somewhat higher than normal. Then this is a blowdown channel from the cooling pond. These little gates that I said could be easily sealed with some dirt shoveled into it. So that's the channel, and even if water drops in the cooling pond, when the cooling water level drops below 13 meters, then that channel doesn't need to be there at all. So it's at 13 meters of elevation. So at the moment it's around 16 meters. It can drop to 13. So we have 3 meters of thickness of water, and the reservoir is about 2 by 3 kilometers. So this is our 100,000, roughly 100,000 million cubic meters of water that we now can spend on cooling the remaining units. So the cooling needs are kind of summarized in here. So right after shutdown, per unit, we have 15 megawatts to dissipate. So this is equivalent to 6 kilograms a second of water being flushed into steam. So this is the equivalent of energy that is needed per unit, right? So we need 6 of those if we are 1 day after shutdown. So we are order of magnitude lower than that at the moment because the units have been shut down for a few months. So the needs are on the order of 1 kilogram of water per unit per second that need to be dissipated to meet the cooling needs. So this is small. I mean, this is already human. Kind of, we can imagine a pipe with one kilograms a second, right? I mean, this is not it's not a garden hose, but maybe a couple of those. So what I'm trying to say is you can imagine kind of DIY situations where you can supply this amount of cooling by other means. So 3 meters of depth, 3 by 2 kilometers gives us this many cubic meters of water, which is worth at this rate for 6 units about two months. So this is 2 months of water being stored in that reservoir. So this is not tomorrow, this is not hours, but this is not also, forget it, it's not a concern. It is limited amount of water. So what about other cooling needs? We talked briefly about spent fuel pools. So this is how reactors look from the inside. So this is where the heat is being produced, so the reactor core. And right nearby, so this is the reactor pressure vessel, and these 3 sections can be flooded with water. And in fact, this is what they do when the reactors are in cold shutdown, preparing or executing refueling operations. So during refueling operations, the entire core will be unloaded in here, and the fresh fuel will be loaded somewhere here, and then some combination of fresh and partially burned fuel will be reloaded back into the reactor. So these pools are relatively small, but again, not negligible. So they can house quite a lot of spent fuel, and there is a lot of water above it to provide both cooling and radiation shielding while doing these operations, because there's lots of people in the containment doing all sorts of maintenance things, and there are operators of the crane that shuffle these fuel assemblies. So there are humans around, so you need appropriate amount of shielding. So there's quite a lot of water, and it will also take days to boil off if nothing else happens. And as I mentioned, these dry cask storage solutions are Western option, so which normally don't reprocess spent fuel. And these are completely passive, so the fuel is cold enough to dissipate its heat by natural circulation of air through the surface of this canister. It needs very little monitoring. It needs no pumping power whatsoever, so it's all natural convection and relatively benign. So we made some assumptions and calculations. There are reports how many of spent fuel assemblies are stored on within containment by the pressure vessel, so in those little ponds. So these are roughly 300 per unit. So there's 2,000 spent fuel assemblies in wet storage which sit there, and they have been discharged from reactor cores a while ago, but they're not cold enough to be put in those dry cask storage canisters. So there are about 2,000 of those. So this is probably another order of magnitude less cooling requirements. Nevertheless, they do sit inside the containment. They are full of radioactive material. They're clad in zirconium cladding, which if overheats and is contacted with steam, will react and make hydrogen and make exothermal energy deposition. So I'm on my last couple of slides. So in anticipation of what's the worst that can happen, I made a slide which is called worst case scenario. So this is a speculation, so bear with me. Now we have all the necessary vocabulary to go through this. So worst case scenario, no makeup water and no pumping power. Like everything is lost. Then what? So first good news. As I mentioned, fission products largely have been decayed. And decay heat is low, so the cooling needs are low. But probably more importantly, the most important radioactive nuclei that causes most nuisance, in particular in Chernobyl and Fukushima, is iodine-131. So it has a half-life of a week, roughly. So since the fuel has been sitting there for quite a while, so the last fission happened several months ago, so iodine-131 is non-existent. So it's completely decayed. It's problematic for two reasons. First, it's volatile. So if it is released, it goes everywhere. Secondly, it's biologically active. It goes into human bodies and accumulates in a single organ, thyroid gland. So it sits there and irradiates your thyroid gland. So according to Chernobyl data, this is the only measurable signal of radiation effects on human bodies that we can confidently measure. So there were thyroid cancer, about 2,000 of thyroid cancer cases with about 60 deaths resulting from those. So this is a measurable effect. Everything else, there are other nuclides that are volatile and will fly away, but they're not as biologically active. They're not as radioactive. And when they do go into the body, they don't stay in the body for a long time. And if they do stay, they stay sort of, spread relatively uniformly throughout the body. So the individual organ dose is relatively low. So we don't have the signal from anything else other than iodine. So that's good news. So as we talked about, cooling requirements are non-zero, but nevertheless they are modest. So they are within kind of not garden hose level, but not too far away from that. Fuel, spent fuel in dry casks, although it is hot, it does cool itself. So it doesn't need pumping power or cooling water. So if they're sitting in extremely robust concrete casks that are very difficult to destroy. Even if you destroy them, the radioactive material that sits there is not hot, so it's not as volatile, and it's all decayed. All important things have already decayed. So the worst thing you can do with spent fuel in dry cask storage is to contaminate some, a parking lot essentially, but not more than that. It's not going to be death of Europe because of compromising integrity of these dry cask storage. So small localized contamination possible, but not life-threatening. What is inside reactor cores is hot, comparatively speaking. It's much colder than it used to be, but it's still hot and it can destroy itself. So if no cooling and no pumping power, then water will gradually boil off. Zirconium will react with water way before the fuel is molten. So zirconium, which holds fuel pellets in fuel pins together, will burn, essentially, releasing additional energy. So the first barrier between fission products and outside world will be destroyed. Luckily, other barriers are still there. So let's talk about those. So zirconium water reaction, hydrogen, which may or may not burn. Dealing with hydrogen is relatively simple. All modern reactors after Fukushima and Chernobyl were equipped with passive autocatalytic hydrogen recombiners. So basically, heat exchangers, air-cooled heat exchangers. Well, they're not heat exchangers, just plates, metal plates with some palladium-based catalyst that will recombine hydrogen and oxygen together in a graceful way, not by burning, but by recombination, and the output product of that is water. They're completely passive. But these are relatively expensive. So other plants opted for just little flames everywhere, so little burners that will burn excess hydrogen. So relatively easy to deal with. Even if it detonates, all the equipment within reactor building is designed to withstand hydrogen burn within the containment. So decay heat is low, but nevertheless it's still there. So again, the same thing applies. Important fission products have already been decayed. some noble gases and cesium-137, which has this annoying half-life of about 30 years, which is not short enough to be decayed by now, but long enough to still sit there and continue to be radioactive. It is volatile, but it's nowhere near as biologically active. We thought it's biologically active, but we haven't seen any signal from that from Chernobyl data. So what's the progression of things? When we produce more heat than we can remove, things heat up. The first thing, zirconium cladding is gone. All the fuel slumps into the bottom of pressure vessel, which then, I mean, it continues to be radioactive and producing heat. So what next can we expect? So various things happen. So popular reactor construction materials. So B4C is in control rods, for example. Stainless steel is what some of the internals of reactor pressure vessel are made of. And most importantly, UO2 is the ceramic that the fuel is in the form of UO2. It's pretty robust, and it takes a while to heat it up and make it melt. So molten core, when I say meltdown, so meltdown is not the scariest thing that can happen. So release of volatile fission products is the scariest thing. And they would be released through, at the much earlier stage. So when the fuel is molten, it doesn't really matter in which form, liquid or solid it is. It will be it will lose its original geometry and will accumulate at the bottom of pressure vessel. If the decay heat removal systems don't work as we postulated, so no power to pumps to circulate that water, and or the heat sink water is not available. So these cooling ponds with sprinkles, which there are many, but they are no longer they no longer have enough cooling water. So pressure vessel water gets to saturation and starts boiling, zirconium-steam reaction, cesium and noble gases escape, core goes down into the lower part of the pressure vessel. If the cavity in which pressure vessel sits, it's like a little pool, if it's flooded, which it is, it will not likely to melt through that pressure vessel. In fact, Russian reactors are slightly more over-designed, and many Eastern European countries that build Russian type PWRs went through this regulatory exercise showing so-called in-vessel retention of molten core, meaning that if there's water on the outer surface of the pressure vessel, then it provides enough cooling to keep the core from melting its way through the wall. So, and then what? So we have all these gases. We have very, very hot, bubbling core inside the pressure vessel. Where does it all go? So the containment building are designed, as we talked about, to hold quite a lot of pressure, and also equipped with dedicated ways of removing that heat from within the containment to the outside world. If those are not available either, then the last option is controlled venting through these stacks and filters that are typically installed in reactors. So it's not 100% containment of radiation, but 90% plus of fission products will be scrubbed by filters, and whatever will escape is largely noble gases, which are, again, biologically meaningless. So the bottom line is that because the cooling needs are relatively modest, and there are many different options by design. So in some reactors, the ultimate heat sink has just one type of, I don't know, heat exchanger and source of cooling water. But in this plant, because it's so big, ironically, it has multiple ways of removing that decay heat. So there's dedicated heat exchanger in little dedicated pools with sprinkles. There is cooling pond with quite a bit of water, which can be also replenished by more kind of industrial pumps. So it's not a large amount of elevation that we need to overcome to bring water from where Dnipro River is now. So it's on the order of 5 meters or so that of head that we need the pumps to provide. Sort of, when there's a flooding in Yorkshire and you have streets flooded, the local services bring these big pumps that can take water from one side of the reservoir to another side of the reservoir. So we're talking these kind of machinery, which is not unimaginable to, in a worst case scenario, to be brought in. And we are not talking about massive contamination of the area where things are still evolving. So I would cautiously be optimistic and definitely against weaponizing the consequences of what might happen. I'm not playing down the consequences. So radiation contamination is a bad thing, which will need cleanup, and a large amount of radiation will kill you. So I'm not saying it's not dangerous, but putting these dangers into proportion, this is probably the most important message of the day, is that we have many options, basically. So there's the cooling needs are modest, and the means to provide these cooling needs are multiple. So these are good news, and even if we lose all of them, the amount of contamination will not result in another Chernobyl or death of Europe. So let's be reasonable. So to summarize what I just said, cooling needs, the real dangers are largely gone. So iodine is no longer there. Cesium is there, but is much less important than we thought. And we have multiple options to deal with that. So I'll stop here. So I promised 45 minutes, so it's 55 minutes, which is not bad. I haven't trialed it. Anyway, I will thank you for your attention and welcome any questions. Yeah, I'm going to unshare the screen and also occasionally look at online questions if you have any. Bob.
Not necessarily directly cooling related. Presumably the containment, the biological shield, are strong enough to resist the sort of weapons that they're flinging at each other at the moment, are they?
So containment's limiting stress is internal, not external.
Yeah.
So it's the energy that should be contained within the containment which is limiting, not the impact of aircraft. So apparently all these containments that were designed to hold this many bar internally can withstand aircraft impact. No problem.
The sort of weapons, the shells that they're using at the moment, presumably are.
It's a new situation. I haven't looked at it into it seriously. Of course.
Honestly, I don't know much about military ordnance, but I would have thought they probably are.
I don't know. But if containment building is destroyed or cannot hold its, perform its function of containment, again, that's not the end of the world.
All the same things you say apply.
Yes. Yeah.
Should we get the microphone for people in the back so people
Sure.
can hear?
Daniel was second, I think.
So you talked about the 3 generators for each reactor, and there's been a lot of the news about the off-site power being lost to the plant. With the lower requirement for cooling, we have 3 to make 1 for each of those reactors. I'm assuming those generators are tied in so that 1 generator could supply multiple reactors.
Usually they're all, I don't know the details, but they are all reconnectable. Mm-hmm. So you can supply power with generator from 1 unit to any other unit. So they're all they're like redundant buses that can deliver that electricity. Another kind of optimistic thing, which in the early days when we were watching the training center was being under attack, there was a discussion about where the fuel for these diesel generators is, and I'm curious because as you know, in Sizewell B, they're all open air tanks that can, in a war situation can be easily compromised. In this design, they're all underground. So diesel storage fuel storage is in underground locations, which makes it slightly less vulnerable to, stray bullets. I'm wondering whether you'll make a recording of this talk. Yes, we are recording this. We will look into this. I cannot promise anything, but yeah, by popular demand, it may be. Any other questions online? Feel free to post in the chat. So clear. Yeah, go ahead. Yeah, arguably, so it's 12 point something meters. The intakes from that pond into where it needs to be are at that level. So the water that is below it is, can still be brought into that with some additional pumping power, like mobile pumps. But the intakes to condensers are at 12 meters, I think. Yeah, that's the reason, as far as I understand. Yeah, over there.
You were just saying how the Sizewell B, for example, is open air. Is there a lot of discussion about changing things in other nuclear plants?
Remains to be seen. I mean, we thought we know everything about nuclear power before Fukushima, for example. And yet every accident like this results in a complete rethinking and complete revolution, if not of the industry, with echoing through. Maybe if it's a reasonable investment, that it could have been considered, around the world, like these hydrogen recombiners in BWRs. Are a popular thing. So controlled venting is everywhere now. Like filtered venting is post Fukushima. So even reactors that didn't have it before, now they all have it. So Swedish reactors, for example, used to have it before Fukushima, famously. Inerting atmosphere in BWR containments by using nitrogen instead of air. That's also a popular option, so that if the core is damaged, or the damage of the core can be minimized if you don't have oxygen around to propagate that zirconium reaction, or hydrogen burn rather. Will the slides be available? Yeah, the same as recording. We will do what we can.
I'd like a copy of that decay heat one for my lectures, if you could.
Oh, it's all over the place. I mean, it's easy. It's easy. So decay heat is obviously dependent on how many fission products you've got in your fuel. So the fuel is fresh, and your brand new reactor just started, operated for 1 day, and then something like that happened, then the decay heat obviously won't be 5% of the nominal. It takes a while for these fission products to build up to the kind of saturation. Saturation meaning you're producing fission products, but you're also removing fission products through their natural decay or because there are neutrons wandering in the reactor core. These fission products will absorb nutrients and become less radioactive or more stable because of that. So after a couple of months of operation, it doesn't matter for how long the reactor was operated before. It can be taken as infinite operation before shutdown. It slightly depends on fuel composition, but PWRs of that type, or PWRs in general, the variations are tiny, so they all around 3% enrichment, 3, 4, 5% enrichment, in which case the relative contribution of different fissile isotopes. So in the beginning, everything is uranium-235 fissions, but as reactors operate, there's larger and larger contribution of other sort of transuranic isotopes like plutonium, and they have different kind of combination of fission products with their own decay constants, and decay heat slightly depends on the composition of the fuel as well, and but not meaningfully. So the order of magnitude that we discussed just now will still hold. So we're talking 0.1% of nominal power that needs to be dissipated, or 1 kilogram per second per reactor of water boiling off. So that's the kind of.
How long does it take for the fuel waste to become completely not dangerous? Because I understand that it's stored there.
Mm-hmm.
Does it take very long?
Yeah, so I think the key point is completely not dangerous. So there are lots of things if you consume with food would be poisonous and dangerous. So
Radioactively dangerous. Harmless.
well, one way of looking at it would be when the chemical toxicity will be greater than radiotoxicity. So I would dare to say or guess that it's probably already now. So all these heavy metals, not just lead, but all heavy metals are pretty chemically toxic. So I mean, if you don't leak it, then just stay away. It's already not dangerous. Another thing on the scale of how radioactive things are, we are talking, the most radioactive, naturally radioactive place on Earth and least radioactive place on Earth where people actually live vary 3 orders of magnitude. So a factor of 1,000. And with no measurable biological effects. So no cancer rates or mortality or no measurable health effects. So the limits are somewhat arbitrary, especially given the science that we know now. I would even say completely arbitrary. So it's a matter of ongoing debate, even though we already have the data. So, rationally, we should just change our, regulatory practices, what we consider dangerous. So, you see what I'm getting? So it's not really. If you eat this, you'll die. Like it's not black and white.
Just trying to think how I can explain this to someone else. I thought you said it was 5% of 3 gigawatt, which gives me 150 megawatts. I'm trying to square that with 1 kilogram per second of water, which is about 2 megawatts. I'm outside factor of 75. I can't think what came wrong in my head.
I think it's the decay power went down even more. Not 5%.
It's 5%
Is
after the reactor.
it's
It's now,
it's 0.5. It's half of 0.1%.
Okay, that's where I believe.
That-
Sorry, the 5%.
Yeah.
Is the initial decay heat a bit higher for BWRs? Because I thought that Fukushima, the drawback figures a bit near 7%, 5%.
Well, so 7% is where your fission, like delayed neutrons, still cause delayed fissions. So you have a minute or so of actually the delayed fissions being overwhelmingly higher than the decay heat itself.
It comes to 5 fairly quickly.
Yeah, but I mean, the longest decay precursors of delayed neutrons are on the order of minutes.
Exactly. Yeah.
So you can't shut down your reactor faster than that.
No.
Let's see, another one. How much control does the rest of the world outside of Russia have over infrastructure of the power plant? What is being done to reduce the threats from artificial intended damages? To be entirely honest, I don't know. What we do know, the International Atomic Energy Agency, IAEA, is taking very proactive role in this. So essentially, they're willingly offering themselves as being essentially a shield. So like nobody will dare to hurt in some way an international delegation of that prominence. So someone suggested on Twitter that Pope should visit nuclear power, so nobody will dare that. And after the Pope, IAEA Director General spending some time in Zaporizhzhia is sort of our next best option, I would argue. So yeah, there are measures, and it's not. I mean, if it was some sort of NATO umbrella, for example, that would have been seen as a hostile action. But United Nations, and IAEA is part of United Nations. This has a different stance, I think. So that's positive. Did those participants online find the talk to be useful? Oh, this is Joe. Yuri said, sure, thank you very much. Adam Davis said yes. Nikitin said yes. Very useful, thanks, Joe. Okay. Killian. Well, they can meet the needs more than way more, because it's all decayed by now.
What are they rated at?
Gigawatts. I mean, these are like multiple gigawatts. I mean, at least 2, maybe 3, maybe 4. I don't know. Like couple gigawatt cooling tower is quite impressive. I mean, if you have a chance to visit any power plant, like thermal power plant, these are very impressive, and you can feel the draft, how the air is being sucked in, and
you can see the tracks cooling down. Even goes by train north of it. You can see the huge cooling towers and tracks.
So for the cooling tower, to the question, to operate, you need both pumping power and you need water supply, because you spray hot water through sprinkles that sit. So it's basically a shower sitting inside a chimney. So these droplets, I mean, you could have just a shower, which is what those sprinkle ponds are. But because you create this natural draft of air, the hot water, droplets are being, mixed with air very efficiently, and water, or a large proportion of it, falls under gravity and recycled, but some is entrained and flies away with the plume of steam.
Store energy. You mentioned it's in cold shutdown, and the zirconium water reaction only happen at high temperature. Given that it's low temperature now, why we still consider that chemical store energy?
Because if you remove heat as it being produced at the same rate, then temperature stays fixed. If for some reason you remove less heat than you're producing, things will heat up. And the longer you have the situation where heat produced and heat removed are not matching, it will go in, I mean, not indefinitely, but until all the things are destroyed and molten.
So one key take-home message is that the over-design of the reactor is very useful.
Yeah, in situations like this. It reminds me of British financial system when in 2008 crisis where US system was very fragile, so everything went crumbling, and more conservative sort of European banks managed to do this because they run their system more conservative, arguably, I don't know, but yeah, so especially the previous generation of nuclear Russian-built nuclear reactors, which produce maybe half the power of those we're talking about, like Slovakia, for example, has 5 of those, and Finland has a couple of those. They are or were over-designed so massively that they all underwent power uprates, pretty substantial power uprates, like, I don't know, 10 more, maybe 20% uprate. Basically the same components or the same volume producing 20% more energy, more power. Yeah, so in situation like this, it's always nice to have over design flexibility. Okay, let's see. Actually, further question. Oh, would you mind going over hydrogen explosion mitigation mechanisms again? You mentioned mini burners and some palladium compounds. What measures were already built in the reactors? I don't know the details. I'm assuming this has been done. It's a routine measure and relatively cheap one.
It's actually normal on PWR rad waste plants to remove the hydrogen anyway.
So
it's usually just a plating catalyst, usually with a control oxygen supply. The hydrogen and the oxygen react on the plating catalyst to produce very, very established technology.
Yes, I agree, and it's fully passive also. It doesn't require cooling needs or pumping power needs. Yeah, and burners are even cheaper because you don't have to spend money on palladium. Yeah, they're literally palladium plated plates, I guess. Yeah. So
very well established technology. So most PWRs have got it anyway on the
and it's relatively easy to retrofit in existing plants. So even those who didn't have it, it's relatively simple to add those. But I don't know the details of the Zaporizhzhia plant specifically. Further question, do you reckon that the current scenario at Zaporizhzhia will provide a further reckoning for industry-wide nuclear safety policy regulations? This is very deep.
yes.
Regulations and requirements, even if consequences from worst-case scenario are low. Well, it's healthy to sit down and reflect. In the aftermath, after things cool down, hopefully. Obviously, we all wish that it ends as soon as possible. For the industry, for operators, for reactor designers, for licensing people, for regulators, to sit down and rethink. Operating nuclear power plants in war zone is not unprecedented, but it's relatively rare. So reactors are not designed to operate in war zone. They can, and they did, and now we reassess things that could happen or might have happened. So it's healthy to learn lessons from this and implement what we can. So
the costs would be frightening, though, to design.
I mean, just like with anything, the amount of dangerous things that can happen are infinite. So you can spend infinite money on safety, and
How much Fukushima is average the cost of new build?
Yeah, so I mean, it's inevitable that both governments and regulators and nuclear industry itself will have some reflection and try to, if not anticipate or redesign things, but learn lessons.
Also, we use, of course, for the anti-nuclear movement, get something else to beat us around the head with.
Yeah.
After the war, will this nuclear site be back online, or is it plan to decommission?
It's hard to imagine without, that's a good question, without the reservoir being replenished with sustainable water supply of these 100,000 million cubic meters of water, with a river which was next door, very easy accessible. Now it's hundreds of meters away, and several meters of elevation to overcome until the dam is repaired, which is, we're looking decades probably, or a decade of work. I mean, this is not easily repairable piece of infrastructure. Until then, it's hard to imagine easily available heat sink. So when I mention multiple options, there's boreholes, like artisan water wells, essentially, that are available, and also the plant is hooked to the Enerhodar city water supply, which, again, in the normal full power operation of all 6 units will be laughable, but when the cooling needs are a kilogram a second per unit, then it could be meaningful. So when I was saying multiple options are available, these are not just mobile pumps to bring Dnipro River closer with some handheld diesel generators, but there are other things that are available as well. Yeah, I forgot to mention that. Better later than never. Okay, anything else? Yeah, I think online also, online people went quiet.
Group picture?
Yeah, group picture. if you insist.
Joe insists.
Is she?
I text.
Oh, right, okay. Well, if Joe insists, then we have to indulge. Will you?
Yeah.
Or maybe I'll go and.
Okay.
I'll sit there.
All right, ready? 3, 2, 1. Okay, thank you.
That was extremely useful. I get asked these questions over and over again. When I wasn't 100%